are three aims of the experiments: to calculate Hall effect, to calculate charge carrier density of the semiconductor that we are using, and to calculate mobility of the semiconductor. The apparatus that we use is the Hall probe, Hall effect setup, which I will be showing you in the laboratory, and electromagnet and a constant power supply. A constant power supply will be there separately for electromagnet and for the semiconductor. And electromagnet requires high current, whereas in the semiconductor you cannot pass that much current. You have to pass a very tiny current, milliamperes, and the voltage developed will be in millivolts. First of all, we will study what is meant by Hall effect. Suppose we have a semiconductor. Here it is shown like a box. Semiconductor is a very small one that we take, but here for now I am showing it like a box, and in a semiconductor, let it be p-type or n-type. Suppose we send current in one direction and we apply the magnetic field in a perpendicular direction. In this case, we are connecting this terminal and this terminal to the battery here, and this is a variable rheostat to vary the current, and this is connected till here to this terminal. That means we are sending the current in this direction. This is the current direction. Suppose we apply a magnetic field in a direction perpendicular to that. That means from above into the board. You have to think it like that. We have shown it like this, but it is three-dimensional. You have to imagine that it is in a direction perpendicular to the current direction. Suppose you keep this type of situation where current and magnetic field are in perpendicular to each other, then the charge carriers will experience a force in a direction perpendicular to this current and magnetic field. That means towards this and this side, electrons and holes get separated. Suppose you take n-type semiconductor, electrons majority carriers and holes minority carriers. They will drift to this side and this side. So a charge will develop to the sides, to this face and this face. And suppose we connect these two sides by a voltmeter. Here I am showing a voltmeter. Here VH is a voltage developed between these two surfaces. This voltage is known as Hall voltage, and there is an electric field established between these two terminals. And observe that T is the thickness of the semiconductor that we are taking. We can either take n-type semiconductor or we can take p-type semiconductor. Suppose you take p-type semiconductor, we get the Hall coefficient to be a positive, and n-type semiconductor we get it to be negative. And in our experiment we are taking n-type semiconductor. And suppose you set up like that. Each time you increase the current. In our experiment what we are doing is, each time we increase the current that we are sending through this, and proportionately the voltage also increases. And we are going to draw a graph between current and voltage, find the relation between current and voltage, and draw a graph. From the graph we are going to calculate Hall coefficient. Theoretically also we are calculating Hall coefficient, practically also we are going to calculate Hall coefficient. From graph also we are going to calculate Hall coefficient, and we are going to compare those two. The formula that we are going to use is, there are three formulae that we are using. First one is Hall coefficient RH. It is denoted by RH is equal to VHZ by IB. VH is a Hall voltage that is developed. Z is a thickness. Actually I have to take Z here instead of T. So VHZ by IB. Z is the thickness of the material, I is the current that you are sending, B is a magnetic field which you are going to set up between the pole pieces just before you send current. That will be a fixed value. Z also is a fixed value. Current and voltage will be changing each time. And the charge density, once you calculate RH, you can calculate charge density N to be equal to 1 by RHE. E is a charge of the electron, RH is a Hall coefficient that we calculated here. So we are going to take this value directly from here and substitute here. E is a charge of the electron, which is a constant. And mobility also is calculated by the formula sigma RH. Mobility sigma value, conductivity value is already given as a fixed value in our experiment, which is equal to 0.1. So mobility is calculated to be sigma into RH. RH value we are going to take from this formula and put it here. And after that, after connecting the circuit like this, we will send the current in steps of 0.5 milliamperes, and each time we increase the current, the voltage increases. Now we draw a graph between current and voltage. Current is a independent variable, voltage is a dependent variable. So current has to be taken along x-axis and voltage has to be taken along y-axis. And we get a straight line graph like this. Take the slope of this graph, which will give you V by I. The Hall coefficient can be calculated by two methods. Theoretically, by directly putting the value of current and voltage in this formula, we can calculate it theoretically, and from graph, by putting the value of the slope in this formula, we can calculate graphically also. So we are going to compare this theoretical value and graphical value. After this, we are going to calculate charge carrier density. We are taking n-type semiconductor, so we are calculating how many electrons are present per meter cube. That is done by n is equal to RHE. That is 1 by RH is a Hall coefficient that we calculated in that, into E is the charge of the electron, which is equal to 1.6 into 10 power minus 90 coulombs. So substitute in this and calculate the charge density. And third one, we are going to calculate mobility also. Mobility is equal to sigma RH, and sigma is the conductivity, which is given to us as a constant value 0.1, and RH is a Hall coefficient, which we substitute from the calculation that we have done. So in this way, we are going to calculate three values here. One is Hall coefficient, second one is carrier density, third one is mobility. This is a theoretical part of the experiment and a vague idea of doing the experiment. Let us see the same experiment in our laboratory and do it actually with the apparatus. You can see the Hall apparatus here. The total apparatus is shown here. And now I will explain each individual part separately. And this one is an electromagnet. What you see here, this is an electromagnet. This total setup is electromagnet. And you can see the two pole pieces inside. These two are the pole pieces. One is north, one is south. And here you have the handle here. Using this handle, suppose I rotate this handle, you can see the pole piece moving towards or away. It can be moved towards or away. In that way, either you are increasing the magnetic field or you are decreasing the magnetic field. And since this is electromagnet, you have to supply the electricity to it. How are you going to supply the electricity? Here we have power supply for electromagnet is there, no? So using that, you are going to supply the electricity to the electromagnet. Now there are two terminals here, red button, red and black. These two terminals here. And to the electromagnet also you can see one red terminal and one black terminal. And here we connect this red terminal to this red terminal and this black terminal to this black terminal. Red terminal to red terminal, black terminal to black terminal. And we measure the magnetic field by using the Gauss meter. Here you see digital flux or Gauss meter. And here you can see 2K and 20K. We will always use this 2K range. We will keep it towards 2K range. And using this set 0, when the Hall probe, this is a Hall probe. See, here you can see this wire end this wire end is going to the probe here. This is a probe and this is called as Hall probe. By using this Hall probe, you will set the value of the magnetic field. And here, when the probe is in air, I use this switch, I use this knob and I will set it to 0 first. This is called as 0 setting. It is showing almost 0. Now it is showing 0, and after setting it to 0, this Hall probe is kept in between the pole pieces without touching the pole pieces. And now this digital meter will show the magnetic field. If you want to increase the field, it is showing 0.318, that is 315 Gauss. But for this experiment I am using more value. So if I want to increase this value, I will increase the power supply to the electromagnet. I will increase the power supply to this using this knob. By using, you can see that the flux meter is showing more and more Gauss. Now I will set it to 1000 Gauss because in this experiment I am using 1000 Gauss. After setting this value, I will remove this Hall probe and I will introduce a semiconductor in between the pole pieces of the electromagnet. As you can see, this is a rectangular strip, and here in the middle you can see the small semiconductor which is in rectangular shape, and you can see 2 metal contacts here and 2 metal contacts here. There are different colors. You can see the different colors over this end, and these two are connected to red and black. These two are connected to the milliammeter here. This is a milliammeter, and the other two are connected to, these two ends are connected through this to the voltmeter, millivoltmeter. 2 ends are connected to 2 opposite ends. These 2 opposite ends are connected to ammeter, and these 2 opposite ends are connected to voltmeter. And we will keep this in between the pole pieces of the magnet, and we observe that whenever you send current in this direction, a voltage will be developed in a direction perpendicular to the current direction and magnetic field direction, that is in this direction. So the Hall voltage that is developed is measured by this voltmeter, and we will increase the current and we will note down the corresponding voltage. Introduce the semiconductor in between the 2 pole pieces, but the semiconductor should not touch the sides of the pole pieces. Like this you will introduce, and you can see the readings changing here. As I increase the current here, you will see that the voltage starts increasing. And so for you just see how much is the maximum voltage that will increase. Here you will see that it is going up to 33. So you can take an interval, this is going up to 3.38 milliamperes. So you can start with 0.5 milliamperes. So each time You increase this to by 0.5. I am starting with 0.5 milliamperes. .59 it is showing. 0.5 and it is showing 5 millivolts. For 0 we are getting 0 millivolts. For 0 milliamperes we are getting 0 millivolts. I am writing it here. For 0 milliamperes I am getting 0 volts. Next I have increased the value to 0.5 milliamperes and the voltage. Here you can see 0.5 milliamperes and the corresponding voltage is 5 millivolts. And now I increase the milliamperes to 1. So 0.98 is almost equal to 1. I am seeing 9.9 millivolts here. And now I increase the value to 1.5. You can observe that the voltage is increasing rapidly. 1.5 milliamperes here and the corresponding voltage you will see 15 millivolts. And now I am increasing this to 2 milliamperes. 2.02 is almost 2. So 2 milliamperes I am getting 20 millivolts. And now I increase to 2.5 milliamperes and I am getting 24 millivolts. Next reading is 3. The corresponding voltage is 29.9. That is the last reading I am getting. I am not getting any further reading, so I stop it here and I will plot a graph between current and voltage.